Today we're going to start with triple integrals, and it's where we're dealing with integrating over a three-dimensional solid, and we're going to see how things change for us, how we can maybe organize things a little bit differently in order to help us as we go through these integrations, and what it is we're actually calculating. So the first thing I want to talk about is this triple integral over e of f of x, y, z dv. So this dv, what this is a three-dimensional volume that we integrate over. And so in order for us to have a three-dimensional volume that we're integrating over, dv has got to be some combination of dx, dy, and dz. And so for integrating over a three-dimensional thing and our integrand is a one-dimensional thing, then put them all together, this gives us a 4D calculation, or result, I should say. And we could say that hypervolume is one example of something that you calculate when you have a triple integral, okay? Another thing that some people might say is that a triple integral, or the fourth dimension, is time, but that's just one application. It's not all that it is. Now, our dv, in the case when we have a region that is like a rectangular box, like this definition right here, B is defined with x values between A and B, y values between C and D, and z values between R and S. If we have something like that, we can just go ahead and write out our integral. We'll have an integrand of some sort. It'll be some f of x, y, z. And then the inner integral goes with the dx, the middle integral goes with the dy, and the outer integral goes with the dz. So as long as we match up the differential with the integral that has the right bounds, it doesn't matter what order that we write these in. And so then we have to wonder, so how many ways do we think we can reorder the differentials? So in double integrals, we had two ways that we could rewrite them. It was dy dx or dx dy. Now we have three things, and so a little bit of probability here. The number of ways to organize three things is equal to 3 factorial, which a factorial just means you take the number that you have and multiply it by all numbers less than it. So 3 factorial is 3 times 2 times 1, which is equal to 6 ways. That's a lot of ways, okay? So this whole idea of like type 1 or type 2, I don't even go there with trying to name them. It's just all the different orders that you could possibly have with dx, dy, and dz. Now the case where x, y, and z are all constants, I've got a picture right here. This is showing us a box, and the box is cut into a whole lot of little pieces. But this is integrating over b when b is equal to the region where x goes from A to B, y goes from C to D, and z goes from R to S. Okay, now we could take each one of those itty bitty boxes and we could examine it, and we could talk about its length, its width, and its height being corresponded with the delta x, delta y, and delta z, and multiply those. And we could even talk about Riemann sums with these triple integrals. We're not going there, but you have to know that that's actually how this is done, is that we would find these itty bitty volumes, and then we would calculate those volumes, multiply them by the function on those volumes or over those volumes, and then add them all up, take a limit on the size of the boxes to be infinitely small, and then sum all those up. And that's a lot of work. So we're just going to go straight to triple integrals and evaluating triple integrals. We're not going to do Riemann sums. Now, if all the bounds are constant, we can use Fubini's theorem, and that guarantees a simple switch in the order of integration if we keep the appropriate bounds with their corresponding differential. So if we switch dx dy dz to dy dz dx, just make sure you switch the integrals accordingly, okay? If your bounds are not constants, do not switch the order. So we are not allowed, so if bounds are not constant, not allowed to simply switch the order without changing the bounds, okay? And that's going to require us to have the ability to draw our region of integration so that we can actually see how things change. So now we have to consider the situation where our region is not a box, our region is some other shape. Actually, before I go there, I should talk about some of the common shapes that we might be integrating over. So common shapes to integrate over. We could see spheres, we could see cones, we could see paraboloids, we could see cylinders, planes, etc. There's just so many. And so some of these shapes may be easier to integrate over if we switch to cylindrical or spherical coordinates. And then just so you know, those are coming up in 15.7 and 15.8. So we will see those. We will see how they help us. And it'll be really cool. All right. So now we're not always integrating over a box. We are integrating over lots of different shapes. And so if we're integrating over a different shape, then we can kind of throw out the idea of the box and focus on the shape that we have. Okay. And so first, we're going to start off with just practicing integrating and how we can organize this so that this isn't a torturous method. And we'll do a couple of problems where we're already given the bounds. Everything's all set up. We don't have to do any work other than integrating. And then we'll work on trying to set up these integrals when it hasn't been done for us. So in this first integral, we are given the integral from 0 to 3, the integral from -1 to 1, the integral from 0 to ln of 2, all applied to e to the x times y plus 2z dx dy dz. So here's what we're going to do. We're going to focus our eyes on the inner integral with the inner differential and call that big A. Then we're going to focus our eyes on the middle integral with the middle differential and call that big B. Then we're going to focus on the outer integral with the outer differential and call that C. The idea here is for us to work on one thing at a time and be able to focus on that one thing. So I'm going to focus on A first. And what I mean by that is I'm actually just going to take the integral from 0 to ln of 2 of e to the x times y plus 2z dx. I'm not writing out the other two integrals. I'm not writing out the other two differentials. I'm focusing on dx, okay? When I'm done doing this, the result that I get will be the new integrand for the middle integral, okay? So let's do this. We're integrating with respect to x, so y plus 2z is a constant multiplier, so let's just focus on e to the x. The integral of e to the x is e to the x. So I've got the e to the x times y plus 2z for my antiderivative. We're evaluating from 0 to ln of 2. So I can factor out the y plus 2z, or just commute my multiplication and focus on evaluating e to the x. And then, so I get e to the ln of 2 minus e to the 0. Now e to the ln of 2, the e and the ln totally undo each other and just leave 2. E to the 0 is 1, and 2 minus 1 is 1. So this simplifies to just be y plus 2z. Okay, now this is the integrand. Let's actually write this in green. This is the integrand for big B. Okay, so now I'm going to go to big B. Big B is the middle integral. So we're doing the integral from minus 1 to 1 of this new integrand, y plus 2z, and then dy. Okay, so I'm focusing on y. My variable is only y, z is a constant. So the antiderivative of y is 1/2 y squared. The integral of 2z with respect to y is just 2yz. We're evaluating from minus 1 to 1 very carefully. The evaluation at 1 gives me 1/2 times 1 squared plus 2 times 1 times z, minus the evaluation at negative 1 gives me 1/2 times negative 1 all squared plus 2 times negative 1 times z. Okay, those ones squared and then the regular one, those are just ones. So we get 1/2 plus 2z, and then the negative 1 squared becomes a positive 1. I distribute the negative from the outside and I get a minus 1/2. The second term is minus 2z. With the negative that gets distributed in, it becomes plus 2z, and this simplifies to just be 4z. Now this that we just calculated is the integrand for c, the outer integral. So now I go to c. I'm going to take the integral from 0 to 3, and here's my integrand, 4z. We're evaluating from 0 to 3. Nope, sorry. We're doing this dz. I got ahead of myself there. All right, the antiderivative of 4z is 2z squared. We're evaluating from 0 to 3. When I plug in 3, I get 9. When I plug in 0, I get 0. So this gives me a grand answer of 18. And that is the answer to the overall triple integral, but just broken into 3 single integrals. So it's a little bit easier for us to focus our eyes on what we're working on in the moment. Okay, so this organization is free to be used on any exam or quiz or whatever in your homework if it helps you. If it doesn't help you, then continue to work through the triple integrals similarly to how we did the double integrals, where we kept writing the outer integral until we were ready to evaluate it. I would also like to add that you can use this organization on a double integral, right? You can label the inner integral as A, the outer integral as B, and then focus on them one integral at a time. All right, the next problem, again, is all set up for us, but now we're not dealing with a box. We are dealing with some region E where, honestly, I don't even know what this looks like. The good thing is I don't need to, because it's already set up for me. I have to trust that they set it up right. I'm just going to evaluate it. Now, I'm going to start with my inner integral. It's from y to x plus y, and that's with dz. I'm going to call that big A. And then my middle integral from 0 to y plus 2, that's with x. I'll call that big B. And then my outer integral, which is 0 to 1, and that's for dy, we'll call that big C. All right, starting with the inner integral, A, we have integral from y to y plus, x plus y. The integrand is 2z minus x, and we're focusing on dz. Okay, the antiderivative of 2z minus x with respect to z is going to be z squared minus xz. We're evaluating from y to x plus y. All right, we'll first plug in x plus y. We have x plus y all squared minus x times x plus y. That's the upper bound. Minus the lower bound, we have y squared minus xy. Okay, I'm going to FOIL out and distribute and try to combine all my like terms. So this gives me x squared plus 2xy plus y squared minus x squared minus xy minus y squared plus xy. I'm noticing that my x squareds go away, my y squareds go away. I have a minus xy and a plus xy, those go away, and I'm finally just left with 2xy. Now remember, this is the integrand for b. All right, so now we work on b. b, the integral is from 0 to y plus 2. Our integrand is 2xy, and now we're focusing on dx. Okay, antiderivative of 2xy with respect to x is going to be x squared y. We're evaluating from 0 to y plus 2. All right, so I'm plugging in y plus 2 for x. That gives me y plus 2 all squared times y minus 0 squared times y. All right, so this gives me y squared plus 4y plus 4 all times y. Distributing, I have y cubed plus 4y squared plus 4y. And this is my integrand for c. All right, so now we go to c. In c, we have the integral from 0 to 1 of y cubed plus 4y squared plus 4y, and this is dy. All right, I go ahead and integrate. I get 1/4 y to the 4th plus, that looks like 4/3 y cubed plus 2y squared from 0 to 1. Evaluating at 1, I get a 1/4 plus a 4/3 plus 2. The evaluation at 0 gives me nothing, no contribution. I can get a common denominator of 12. The first fraction would be multiplied by 3. The second one would be multiplied by 4, so it's 3 plus 16. And the third fraction would get multiplied by 12, so I get 2 times 12 is 24. This adds up to 43 over 12. You can also just plug those fractions into your calculator and make sure that your calculator can give you a fraction answer, not a decimal, because it will be an approximation if it's a decimal. Okay, get a fraction. So that's it. This is actually such a nice method because it really allows you to focus on just one piece at a time. Triple integrals are a lot of work. Yes, it is 3 integrations, but if you can keep your work organized, you can follow what you're doing, you'll get there. You'll get where you need to go. Mistakes will happen, though. They definitely will. So go slow enough by actually writing everything down so that you can see when you've made a mistake when you try to find it. All right, next problem. We're supposed to write 2 iterated integrals. When we call an integral iterated, that just means that the bounds are written into it. So we're being asked to write 2 iterated integrals for the triple integral over e of x dv, where e is the region in the first octant bounded by the plane x plus 2y plus 4z is equal to 8. And they've chosen differential orders for us. We're looking at dx, dy, dz. And then we're also looking at dz, dy, dx. And then we're not going to evaluate. We are just going to set these up. All right. So we're in the first octant, and we have a region that's bounded by a plane. So I think first things first, I should probably draw my region. In fact, that's always the first step, is to draw the region if you're able to. And so I have a plane. I'm going to draw the intercepts for my plane. And let's see, draw an octant first. So in order to get my intercepts, for example, for the x-intercept, I let y and z be 0, and then I solve for x. I get x is equal to 8. So I'm going to put an 8 all the way down here. If I want my y-intercept, I let x and z be 0, and then I solve 2y equals 8, which means y is equal to 4. And if I want my z-intercept, I let x and y be 0, and I solve for z in 4z equals 8, and I get z is equal to 2. Now I can connect these dots that I'm about to draw, all my intercepts, and here's my plane in the first octant. When we're told the first octant, that means that the xy plane is part of the closure of our bounds. The YZ plane, the XZ plane, all the planes are actually helping close up this triangular prism-like shape. We want to come up with how we set up our bounds in order to set up a full integral. I'm going to focus on the dz, dy, dx one first, because for some reason it ends up being a little bit easier to understand. So for dz, dy, dx, the first thing I'm going to consider here is that if dz is coming first, then I need a lower z value, and so that's going to be the floor for z. The floor in terms of height is the xy plane, which is z equals 0. The ceiling for z, so again, we're doing height, we're going vertical. So if I'm standing at any given point, let me just go ahead and put my floor in. If I'm standing anywhere on the floor there, and I look up, my ceiling is slanted. And the ceiling is slanted because my ceiling is the equation of the plane. So the ceiling for z is this plane, but I have to solve for z. I can't just write it as x plus 2y plus 4z equals 8. No, I need to solve for z. So it's z equals 8 minus x minus 2y over 4. I can also write that as 2 minus x over 4 minus y over 2. Either way is the same, okay? All right, so what that means is for dz, my integral bounds, I've got 0 as the lower bound, and then 2 minus x over 4 minus y over 2 is the upper bound. Okay, now the dy dx part. So this is my dz part. Yay, that's done. So now we're going to focus on the subset. We're going to look at dy dx, okay? dy dx, that's x and y. How do they play together? I need to look at the xy plane. So if I'm working with dy dx and I've already dealt with dz, then we're going to let z equal 0 in the plane. Then we get x plus 2y is equal to 8. That will be the equation of my plane as a line in the xy plane. So let's see what that looks like. Well, funny enough, we actually already have this. I'm going to draw a green line over it so you see it. We already have our triangle. We already have our region drawn in the octant. We can just kind of transfer that over to this xy plane. And so I've got an intercept on the x-axis at 8 and on the y-axis at 4. I can go ahead and draw my intercepts, connect the dots, and here's my region. Okay, so let's see, what order do we need to go in? It looks like dy comes first, which means y should go from a function to a function. The equation of this line is x plus 2y is equal to 8. I don't have to do any work to get that. It's coming for free from the plane when we let z equal 0. However, I do need to solve for y. So y will be equal to 8 minus x over 2, or 4 minus x over 2. Okay? So now I can see here that y goes from 0 up to the line 4 minus x over 2, and x is the constant. It's going from 0 to 8. So if I want to write this triple integral over e of x dv as an iterated integral with the order of dz, dy, dx, just write these out. I've got x, dz, dy, dx. Then the innermost integral is the z values. They go from 0 to 2 minus x over 4 minus y over 2. dy goes with the middle integral, and those are going from 0 to 4 minus x over 2. And then my outer integral goes with x, and those are going from 0 to 8. And so now I would just integrate this the same way we did in the previous two problems. Now, unfortunately, that's not all that was asked for. We were also asked to find how to set things up if the order is dx, dy, dz. Okay, so for dx, dy, dz, I'm dealing with dx first. That means I need to find a building where I've got a floor for x and a ceiling for x. Now, x equals 0 is corresponding with the YZ plane, and that's where x starts since we are in the first octant. So we really are starting on the YZ plane where x is equal to 0, and then kind of think of coming out of the screen, and as you come out of the screen, you're going to hit the plane again. So the lower bound for x, I should say the floor for x, is x equals 0. And the ceiling for x is, well, now I need to solve for x in the plane. We have x plus 2y plus 4z is 8, so just move everything over, leave the x alone. We get x equals 8 minus 2y minus 4z. So we've got our floor and our ceiling. This just means that for our bounds, 0 is the lower value for x, and the upper value is 8 minus 2y minus 4z. Okay, that takes care of dx. Okay, once I'm done with dx, I can go ahead and deal with dy dz. We'll do a different color for this. So dy dz, this is where we let x equals 0 in the plane. And if we do that, then what we have is 2y plus 4z is equal to 8. That's going to be the equation of the line that we see. Now I want you to look back up at our drawing. Remember when I drew the floor for x, it was on the YZ plane. That's actually our two-dimensional projection that we need. It's already drawn for us. Let's just transfer it to a 2D quadrant. So we've got the YZ quadrant. We have an intercept at 4 on the y-axis and 2 on the z-axis. And then we can go ahead and draw in our line. And this is our region. The equation of this line is 2y plus 4z is equal to 8. Now I need to figure out which variable I should be solving for. We're going in the order dy dz. That means z can go from a constant to a constant. So I can already see the z is going to go from 0, I don't know why I wrote y, 0 up to 2. But y is going to go from a function to a function. So that means I should solve for this line in terms of y. Y is equal to 8 minus 4z over 2. And that simplifies. So I'll write that in its simplified form up here. So y is going from 0 up to 4 minus 2z. All right, we have all of our bounds. We can go ahead and say that the triple integral over e of x dv is, I'll write my 3 integrals and an x and a dx, dy, dz. My x bounds, those are from 0 to 8 minus 2y minus 4z. And then my y bounds for dy is the middle integral. We go from 0 to 4 minus 2z. And for dz, we're going from 0 to 2. And that's it. And we integrate as we did in the previous problem. So planes aren't that bad. We just did 2 orders of integration. Please keep in mind there are 6 orders of integration. So we can look at all the possible combinations of dx, dy, dz in all the different orders. Okay? In this next problem, nicely enough, we have a nice picture drawn for us. And I really like this problem because it's going to make us focus on what happens if we end up with something that's circular in the last two integrals. Okay, so let's focus on what we have here first. We have a triple integral over e of the square root of x squared plus z squared dv. E is the region that's bounded by the paraboloid y equals x squared plus z squared. And they've drawn that for us here in the first picture. A paraboloid, as you know, is not bounded. It's open, but ours is closed because there's also the plane y equals 4. That's this closure right here. Okay, so we're looking at the intersection of the plane and the paraboloid being the closure. And we're going to integrate over that. Now, we have to pick our order of integration, okay? Now, because sometimes this is the reason, because of the ugliness of the integrand in terms of x and z, let's integrate with respect to y first. Okay, so then that means we're either going to do dy and then dx dz, or dy dz dx, and we'll decide once we get there. Okay, we're not going to figure it out all at once. We'll do one thing at a time. Okay, so if I do y first, I have to look at a floor and a ceiling for this. Now, on this particular problem, the smallest y value is 0, but that value 0 is occurring on the paraboloid. It's not the plane y equals 0. It's just the vertex of a paraboloid. So our smallest, or the floor for y, so let's say for dy, we have the floor for y is not 0. The floor for y is the equation of the paraboloid. It's y equals x squared plus z squared. Because depending on what your x and z values are, you're not starting at the origin, right? You're starting on the paraboloid and then moving outward along the positive y-axis until you get to the ceiling for y. So the ceiling for y is, well, it's that plane. It's where things get cut off, and that's y equals 4. Okay, so we have a lower bound for y, that's x squared plus z squared, and we have an upper bound for y, and that's 4. That will take care of dy. Okay, now what we're supposed to do is we're supposed to take that image and we're supposed to project onto the xz plane. Okay, so imagine standing on the y-axis and looking at this shape. All you're going to see actually is a circle. That circle will be the projection onto the xz plane. So for dx dz, project the paraboloid onto the xz plane. And what you're going to see is the intersection of the paraboloid and the plane, which will be this, if we look at the intersection of those, that means we will see x squared plus z squared is equal to 4. That's like the biggest part of the paraboloid, is that part that's on the far right. And so if we were to shine a flashlight on that, the shadow onto the xz plane would be that circle. Okay, so our region of integration, this is it right here. This takes care of dx dz, this third image. The second image actually doesn't help us with anything. That would be doing our integration in a different order. But the third image is what we need for dx dz. We're seeing a circle. It's the circle x squared plus z squared equals 4. And so since we're doing, well, we can do dx dz or dz dx, either or. Okay, I'm going to do dz dx actually. And so for, I guess we'll highlight that. Let's go ahead and do that one. So in order to do dz dx, let's see, let's just draw this really quick. All right, we've got a radius of 2. The equation of, oh goodness, we have to go from the bottom of the circle to the top of the circle. The top of the circle we could call, if we solve for z, z is equal to the positive square root of 4 minus x squared. The bottom of the circle is z is equal to minus the square root of 4 minus x squared. And then x goes from minus 2 to 2. Okay, so here's how we set this up. We have our triple integral over e of the square root of x squared plus z squared dv is equal to the integral. My outer integral, that's going to be x, so I go minus 2 to 2. My middle integral is going to be from the lower z value, the negative 4 minus x squared, to my upper z value, which is the positive square root of 4 minus x squared. My innermost integral, that's y, we already wrote that up, so the lower bound is x squared plus z squared. The upper bound is 4. And then my integrand is still x squared plus z squared. And the order we have here is dy, dz, dx. Okay, that looks awful. It really does. However, because I'm integrating with respect to y first, that square root of x squared plus z squared is just a constant. So I'm going to focus on this first. Okay? We'll call this a, and then we'll get back to it. So with a, we're looking at the integral from x squared plus z squared up to 4 of the square root of x squared plus z squared dy. The antiderivative is going to be the square root of x squared plus z squared times y, evaluated from x squared plus z squared up to 4. Okay, when I plug in my evaluations, I get the square root of x squared plus z squared times 4 minus the quantity of x squared plus z squared. Okay. Let's put that back in. So now our integral is going to be the integral from minus 2 to 2, the integral from minus square root 4 minus x squared to positive square root 4 minus x squared of the square root of x squared plus z squared times 4 minus, in quantity, x squared plus z squared. And this is dz dx. Okay, I'm looking at this and I don't know how to integrate it. I can't. There are no techniques that are going to help me here. However, this region of integration is a circle. And if you have a region of integration that is any part of a circle, think polar. Once you get down to 2 integrals left, you can switch over to polar. Now I realize it's a little off because we have an x-axis and a z-axis, but that's okay. We can still switch to polar because it's just 2 variables. They're in rectangular. We want to get to something else, r's and thetas. So what if we're gonna go ahead and let x equal r cosine of theta, z equal r sine of theta, x squared plus z squared is going to equal r squared, and we have a full circle, so the bounds, let's see, it's a full circle, but the radius is 2, so we're going to have our bounds for r, it's going to go from 0 to 2, and the bounds for theta go full circle, theta goes from 0 to 2 pi. And that will actually make things a lot better. Okay, so these bounds right here for my dz dx, we're not going to like plug in r cosine theta for x there. We're just going to switch to r's and thetas. We already found the bounds, okay? Remember, you never actually take rectangular iterated integrals and start plugging in x's and y's. You draw your region. You notice your region is circular. You figure out the r and the theta values you need to have take on in order to get whatever part of the circle you're dealing with. Okay, so in polar, let's see. In polar, this is equal to, I'm going to write up my integrals. I'm not sure what order I want to go in yet, so I'm going to leave them indefinite for now. But in my integrand, everywhere there's an x squared plus a z squared, I'm going to replace it with an r squared. So I have the square root of r squared. I have 4 minus r squared. Oh, wait a second. We also need that dz dx is equal to r dr d theta. So my dz dx gets replaced by the r dr d theta. So I guess I've chosen my order. R is going to be the inner integral from 0 to 2. Theta is going to be the outer integral from 0 to 2 pi. Now I need to clean this up. That square root of r squared is just an r. I have another r on the other side of the 4 minus r squared. So I have an r squared in there. When I rewrite this, 0 to 2 pi, 0 to 2. So if I distribute an r squared into the 4 minus r squared, I get 4r squared minus r to the 4th. dr d theta. This is something I can integrate. This is easy, totally easy. So let's do it. And with this one, I'm not going to worry about that organization of the a's and the b's. I'm just going to go ahead and do this one. So I get the integral from 0 to 2 pi. Antiderivative with respect to r is 4/3 r cubed minus 1/5 r to the 5th from 0 to 2. And then d theta. If I evaluate, I get 0 to 2 pi, 4/3 times 2 cubed minus 1/5 times 2 to the 5th, and then minus 0, d theta. The 4/3, the 2 cubed is an 8, and 8 times 4 is going to give me 32 over 3. 2 to the 5th is 32, so I get minus 32 over 5, d theta. That simplifies to be 64 over, whoops, I still have my integral, 0 to 2 pi, 64 over 15 d theta. Okay, so that's just a constant. When I integrate, I'm just going to get a theta. So this is equal to 64 over 15 theta from 0 to 2 pi. If I replace that theta with a 2 pi, I now have 128 pi over 15. Okay, that was kind of a long problem, right? Not impossible, but long. And it was a lot of it was just building up. Like, how do we do this setup? How do we get this, put together? Now, what we did by switching the outer two integrals to polar is we actually forced what's called a cylindrical coordinates transformation without even knowing it. So before we even get to 15.7, where we're dealing with the cylindrical coordinates, I've already showed it to you. It's really, I don't want to call it simple because I'm sure it's not simple for everyone, but it's pretty straightforward. The idea is that one of the variables is rectangular and the other two are polar. Okay, in this case, y was in rectangular and x and z were in polar because they had a circular relationship. And that's kind of how it works. All right, let's look at another one. We're supposed to just write this as an integral. We're not actually being asked to evaluate. So these next two problems are really just setting up so that we're practicing that and getting more comfortable with it. So in number 5, we're supposed to write the triple integral over e of x dv as an iterated integral where e is bounded by the paraboloid x equals 4y squared plus 4z squared and the plane x equals 4. Okay? So this one, the paraboloid, we remember what those look like. This is a paraboloid that is coming out the x-axis, and its circular region is y and z playing together. So let's see if I can draw this. There's my circular region. It's hard to do. Something like that. That's a terrible paraboloid, but you know, it is what it is. Something like that. Okay, the point is its vertex is on the origin and then it's opening out along the x-axis. Okay, and then we're told the plane x equals 4 is where it stops. So that's like a cap that's on it. Okay, that's x equals 4. Okay, so x-axis, y-axis, and z-axis. This problem is actually very, very similar to the previous problem because, again, we're dealing with a paraboloid. It's just facing out a different axis. And so that's the point of this, is just to show you when it's rearranged. Okay, so I'm seeing right here x is a paraboloid and x is a plane. Those are my bounds for x. And the one that comes first is the paraboloid, and then we walk out the x-axis towards the x equals 4 plane. And so that's telling me that 4y squared plus 4z squared is less than or equal to x, which is less than or equal to 4. So I want my dv to be equal to dx first. And then I can decide if it's dy dz or dz dy. I'm thinking it'll probably be dz dy. We'll let it do that. Okay. So I have my bounds for x. Now what I want to do is I want to take that circle that we're seeing where the plane cuts off the paraboloid and project that onto the yz plane. So we're going to project 4y squared plus 4z squared equals 4 onto the yz plane. Now, why is it equal to 4? Because what I'm doing is I'm taking the intersection. I'm taking the equation of the paraboloid and I'm setting it equal to the equation of the plane, since they are both x equals. When I do that, I can now divide everything by 4, and we see that this is y squared plus z squared is equal to 1, a unit circle. So I'm going to draw that on the yz plane. I don't need to draw it very big. And this is y, and this is z. Okay? So very similar to the previous problem where we have to go from a lower bound of z. We could have z equals the negative square root of 1 minus y squared. And the upper part, the upper semicircle, is going to be z equals the positive square root of 1 minus y squared. And then y goes from negative 1 to 1. Okay, so let's just write that out. The lower bound for z is the negative square root of 1 minus y squared. That's the lower semicircle. And then the upper bound is the upper semicircle, the square root of 1 minus y squared. Well, y goes from negative 1 to 1. All right, so I can go ahead and rewrite this. My triple integral over e of x dv is equal to a triple integral. Outer integral is negative 1 to 1. The middle integral is the negative square root of 1 minus y squared up to the positive square root of 1 minus y squared. And then my most inner integral is going to be 4y squared plus 4z squared, and that's going to go up to 4. And my integrand is x, and we're doing this in dx, dz, dy. Now, what you want to notice is that the dx portion, that comes first and is in rectangular coordinates. We're going to just keep it in x. But then when we get to the dz and the dy, we're going to switch to polar again. Okay? So slightly different setup than the previous one, but it's still pretty much the same problem, right? It's weird to look at because we're doing x is in rectangular and y and z are in polar. So when y and z are in polar, let's see, if we look at our axes, it looks like y should be r cosine theta, and z will be r sine theta. We'll have that y squared plus z squared is equal to r squared, and we'll have that dz dy is r dr d theta. So those will be our replacements when we put them in. Our integrand, well, we'd have to go ahead and integrate and see what it would be, but once we do the inner integral and we simplify it and everything, we'll see what's left, and then that'll need to be converted to polar as well. Okay. Now, it turns out that if you wish to find the volume of a solid, you can do so by just using a triple integral, as long as the integrand is 1. Because normally a triple integral is calculating some fourth dimensional thing, but if the integrand is 1, then we've got dv, which is volume, times a 1. Well, 1 times volume equals volume. It also equals that fourth dimensional thing, but it's like a tricky way to go ahead and calculate volume. So before we were using double integrals to calculate volume, but we can also use triple integrals to calculate volume. So always pay attention to what's being asked of you. Like I might specifically say, write up a triple integral, which would calculate volume. Okay, that means your integrand is 1. When you see this, write up a triple integral, which would calculate the volume. You have to know right away, this means the integrand is equal to 1, okay? All right, and we're trying to find the volume of the solid that's enclosed by this cylinder, y equals x squared, and the planes z equals 0. That's the xy plane. And then the plane y plus z equals 1. All right, so I need to draw this because I'm not sure how to set it up first, and that's all we're doing is going to set it up. So I'm going to draw my octant. Okay, I'm going to draw my plane as a line first. Okay, y plus z equals 1 has a y-intercept at 1 and a z-intercept at 1 as well. So I could connect those dots. Okay, this plane will go into the screen and out of the screen. It's going to run parallel to the x-axis, but for right now I'm just going to draw the line itself. I also want to draw the line of z equals 0, which in 2D would just be the y-axis, but we know in 3D is the whole xy plane. Okay, now y equals x squared is a parabola, and this is kind of funky, but it's a parabola that has its vertex at the origin, and now I'm just kind of drawing this on the xy plane. I know that it has this shape here, right? That's a parabola. And then, well, it looks like I can only go so far as 1, though, along the y-axis, because that plane is going to cut off my parabola. Now, it's not actually parabola, it's a parabolic cylinder. And this parabolic cylinder, y equals x squared, is parallel to the z-axis, which means we would see a cylinder running up and down along the z-axis. But we have 2 planes cutting it off. We have the xy plane cutting it off, and we have the y plus z equals 1 plane cutting it off. So now I can go back to my y plus z equals 1, and I'm going to draw a little bit more of it where it cuts off my cylinder. Okay, so it's a little hard to imagine this, but we could imagine this cylinder coming up and then running into that plane, and that's as much as we can get. It's kind of shaped like a cheese wedge. I think food helps me see shapes in Calc 3. All right, so we have to come up with how we should write a triple integral for volume. Number 1, let's write out our 3 integrals, and let's write out our integrand. Since it's volume and using a triple integral, we know that the integrand is 1. Now we have to figure out what order should we go in. This problem actually very nicely lends itself well to doing dz first. Okay, so the floor for z is, well, it's the xy plane, it's z equals 0. And the ceiling for z is that orange plane, that's the y plus z equals 1, which we would solve for z, and z is equal to 1 minus y. So I can go ahead and put in 0 to 1 minus y for my bounds for z, okay? Now I want to project this shape onto the xy plane. On the xy plane, I can already see it. It's a parabola. I already drew it, right? But it only goes as high as 1. So we've got this shape going on here. And then it's capped off. Okay. So it looks like we've got y equals x squared as a lower bound for y. And then we have y equals 1 as an upper bound for y. So we'd have x squared less than or equal to y less than or equal to 1. And at the same time, x is going from -1 up to 1. So those are our bounds. Lower bound for the middle integral, we'll do x squared to 1, so that will go with dy. And for x, we have -1 to 1, that'll go with dx. This is our integral. This will calculate the volume of that cheese wedge that we've got there, okay? All right, so the next thing we can talk about is mass, moments, and center of mass of a solid object with a variable density. These are super tedious. I don't actually test over these, but I definitely do give a little bit of homework. I think there's like one problem, and that is because you will have to calculate 4 triple integrals in order to calculate the center of mass, and it's just painful. However, it's not hard, it's just tedious, okay? Our mass is just as we saw it in 2D. We're integrating the density function over a 3-dimensional solid lamina, okay? The moment about the xy plane, that's a little bit different. So before we were looking at moments about axes, now we're looking at moments about planes. And so it's that tendency to rotate about a plane. So the moment about the xy plane means we need to multiply a z with our density function. And then it's the exact same setup as the mass. The moment about the xz plane means we need to multiply the density function with a y, and then everything else is the same. Moment about the yz plane, multiply by an x with the density function, and then integrate. Center of mass, the x bar is the moment about yz over the mass, y bar is the moment about xz over mass, and the z bar is the moment about xy over mass. These formulas are on your formula sheet. You do not need to memorize them. You just need to know how to calculate them, okay? If you have any questions on your homework, please reach out. Send me a picture or whatever it is you need and get your questions answered.